Okay, hello. I'm going to go through and do a walkthrough of the GCSE Trilogy Chemistry Foundation Paper 2 from June 2022. Ideally, you'll have already had a go at this paper and you're using this to help mark and work out why your answer is correct or incorrect. So, first one is to draw a bar on a graph, which is quite a nice task to get us going. It tells us that Earth's atmosphere contains 21% oxygen, and to add that bar to the graph, each of these goes up in twos. So we're going to draw a bar from oxygen up. It doesn't really matter how big the bar is as long as the bar exists. And always use pencil to do this. So try and make sure it's halfway. You get plus or minus half a small square for the marking in this, and that takes up to 21. You don't need to shade it in as long as the bar is there. And number two, what is used to test for oxygen gas? For a burning splint, that is a test for hydrogen. Damp litmus paper is used to test for chlorine. Lime water is used to test for carbon dioxide. And a glowing splint is our correct answer, used to test for oxygen. And number three gives us two pie charts that we've got to read to work out what has happened over time in the Earth's atmosphere. It tells us to use the words in this box to help us answer the two questions. You can use each answer more than once or not at all. Since the Earth's early atmosphere, percentage of nitrogen in the Earth's atmosphere has gone from small amounts to 78%, so that has increased. In the same time, the percentage of oxygen, well, oxygen's not even on this pie chart, now being 21%, so this is also increased. You get 1 mark for each of those. On page 4, question 1.4, it's asked us, why has the percentage of carbon dioxide decreased since the Earth's early atmosphere? Well, volcanic activity caused an increase in nitrogen. Industrialization is a more recent development, and that is increase in CO2 since about the 1800s. The answer for both for these 2 marks is dissolved in the oceans and formation of sedimentary rocks. You get 1 mark for each tick that you put down. We've now got another graph to read, a different type of graph this time, which is a line graph, and we're asked which 2 times have the highest concentrations of oxides of nitrogen in the atmosphere. So this tells our concentrations on the y-axis, so it's going to be this point and this point, which is 9 a.m. and 5 p.m. Suggest reasons why, and this tells us that these are produced when nitrogen reacts with oxygen in car engines. So it's because there's more cars on the road. You could also say buses, lorries, traffic, but there's more cars, there's more vehicles on the road at these times. Okay, we're going to go to page 6, which is the start of question 2. And this question is about fuels. Coal deposits were formed from the remains of trees. What process in the leaves of trees uses carbon dioxide? That is photosynthesis. Ideally, we want this to be spelt correctly, but if it is incorrect, it has to be obvious what the word you meant was. How is coal formed after trees died? This is because the trees are compressed over time. So the trees die, and the pressure from the rocks above compresses them down, which forms coal eventually. Coal contains small amounts of sulfur. Name the gas produced when sulfur burns in oxygen, and this is called sulfur dioxide. It's the same way as we have carbon dioxide, we have sulfur dioxide, and it does ask you for the name for this one. Give 2 problems caused when this gas, by this gas. So one problem is acid rain. Sulfur dioxide reacts with moisture in the clouds to produce that. Acid rain can then destroy buildings and statues, etc. So you could have said that as well. And then respiratory problems or breathing issues. So again, respiratory problems or any kind of breathing issue was allowed for that one. 2.5 on the next page, we've got another graph that we have to read and describe what happens to the amount of fuels used to generate electricity in the UK from 2012 to 2018. So, mark number 1. We have less fossil fuels used. So that's the stripy one here. Mark number 2. We have more renewable fuels used. That is the clear box. And number 3, nuclear stays the same. So the use of nuclear fuels has stayed the same. Other fuels stay the same. And you can get 1 mark for either of these. So that was an or between nuclear and other fuels. Cool, we're firing through. We are on to question 3. Question 3 is about ammonia and its compounds, and we've heated a sample of ammonium chloride and been given the equation for the reaction. We need to name this product HCl. This is hydrogen chloride, or, and this was the answer I put, hydrochloric acid was allowed. Because we're not told what the state is, we could assume that it was aqueous for hydrochloric acid. Ammonia is a gas. What is the state symbol for ammonia? It must be G. This is for a solution, or aqueous. This is for a liquid, for example, water. And this would be for a solid, for example, carbon. How does the equation show the reaction is reversible? This symbol, where we've got an arrow, half an arrow pointing in each direction, shows that it is reversible. So the reversible reaction symbol is used. Finally, if the forward reaction is endothermic, the reverse reaction must be the opposite, which is exothermic. So not many options for these questions, just kind of that is the answer. Complete the sentence using an answer from the box below. Equilibrium is reached when the forward and reverse reactions happen at exactly the same rate. So equilibrium is about having reactions at the same rate in a closed system, so a closed vessel where nothing external can change that. We are still on question 3. We're now labelling a reaction profile. This is kind of linked to paper 1, but is obviously seen on paper 2 as well. Which letter represents the activation energy of further reaction with a catalyst? So A tells us overall energy change. B isn't really a thing at all. D is the activation energy with no catalyst. And how do we know that? Well, a catalyst will lower the activation energy of a reaction, so it must be C that is our activation energy with a catalyst. I give one reason why using a catalyst reduces costs. Do not answer in terms of the activation energy. There is 3 options available. It increases the rate, or you could say it decreases energy use, or a lower temperature can be used. I would be careful with that one because that would decrease the rate of reaction, so it is a balance between these things. Finally, ammonia is in a mixture that is used as a household cleaner. What is a mixture designed as a useful product called? This is called a formulation. So things like household cleaners, makeup, paint are all examples of formulations. Right, question 4 gives us some information and then a question as well. So I'll quickly show us this. This is called the disappearing cross experiment. They're investigating the effect of concentration on the rate of reaction between sodium thiosulfate and hydrochloric acid, and they're timing how long it takes for the cross to no longer be seen. They're using sodium thiosulfate in a conical flask, adding hydrochloric acid and starting the timer. They then repeat with different concentrations of sodium thiosulfate. Now the dependent variable and independent variable, dependent is what we measure and record. So this is what we're writing on our results table while we're doing the experiment. The independent is what we choose to change. So we are choosing our different independent variables, and these have set values that we have chosen before the start of the experiment. So our dependent variable is going to be the time for the cross to no longer be seen, because we are recording that and that changes with every experiment. The independent is the concentration of sodium thiosulfate, and the fact that we're repeating with different concentrations of sodium thiosulfate helps tell us that. That is what we are choosing each time, whether it's 0.1, 0.2 moles, whatever. Number 14 is always a nice one that we see. It's to tell us what the temperature on the thermometer is, and it is 19.5. Each of these little dashes represents 0.1 degrees C. Now we do always get a graph to draw, and I will try and show you this together. So when we're drawing a graph, please use a pencil, please use a ruler, and please be as accurate as you can be. You do only get plus or minus half a small square off kind of in your placement. Do not automatically put a 0, 0 on this unless you're told to do so. So 0.1 moles per decimeter cubed is going to go to 82, and all of these go up in 2, so we're going to go all the way up to 80 and put across at 82. 0.2 is at 40. 0.3 is at 20. You do normally find that at least some of the points are at nice cross junctions. So 10, 12, 13 for 0.4. 0.5 is at 10, again a nice cross junction. And 0.6 is at 8. We get 2 marks for plotting all these points correctly. If you get 4 or 5 points correct, you would still get 1 mark. Any less than 4 points correct, you would not get a mark at all. We're also asked to draw a line of best fit. And for the rate of reaction, this is often a curve, and this does look like it's going to be a nice curve here. And this is where using a pencil is really important, just in case you slip up like I almost have there, and maybe don't quite draw an accurate line of best fit. So something like that should be okay. Predict the time taken for the cross no longer be seen at concentration of 0.7 moles per decimeter cubed. So I've actually already extended this line because I knew this question was coming, and we want that line to be extended kind of past here as best we can. And our time is going to be about 7 seconds. If you've got a massively wrong line of best fit, you'll obviously lose a mark on 4.3, but you can still gain the mark on 4.4 if you've used your line that you've given correctly. 4.5, as the concentration of sodium thiosulfate solution increases, the time taken for the cross no longer to be seen will decrease as well. And we can see that in the graph that we've been given. So decreases. Cool. We're still on question 4. We've got a little calculation to do, and it gives us a formula to calculate the mean rate of reaction, and the information is in the question that we need. So we get 1 mark for saying the mean rate is equal to 0.725 divided by 20, so that's mark number 1. And mark number 2 is for getting our answer, which is 0.03625 on here. You don't need a unit in this occasion because that's what the next question is. If you gave a unit, that would just be ignored. So it's asked you, what is the unit for this? Well, we've got grams at the top. We've got seconds on the bottom. So that's going to simplify down to G/S. 17, we've got another calculation. This time it's looking at the mean value. Do not include the anomaly in your calculation. Give your answer to 3 significant figures. This is our anomaly, so we're not going to include that. So we're going to have 60.5, sorry, plus 63.2, plus 65.7. Divide that all through by 3. I normally show my different steps of working just in case I type something into my calculator wrong. So I'd have 189.4 divided by 3, which gives me an answer 63.13333, etc. We get 1 mark here, we get a second mark here, and we get a third mark for rounding that to 3 significant figures, which would be 63.1 seconds. Question 5, we're on to organic chemistry. It says that this is a hydrocarbon. Complete the formula of this hydrocarbon shown here. 1, 2, 3 carbons. 1, 2, 3, 4, 5, 6, 7, 8 carbons. What is the name of the carbon in figure 9? Now this is a little bit of us having to recognise this. We have 3 carbons in a row, which is going to tell us it begins with prop. We only have single bonds, so it must end in ANE, and that links into the next question. This is an alkane. So the homologous series is the same as the family of compounds, and we only have alkane, or alkene to choose from. It must be one of these two. 5.4, we've got kind of linked to calculation math skills. 30 grams of another hydrocarbon contains 24 grams of carbon. Which calculation shows the correct, which calculation gives the percentage of carbon in the hydrocarbon? Well, if 24 grams is carbon, 30 is the total, and to get it to percent, we'll times by 100. It must be this answer that we have. And this one is actually quite common. I've seen it quite a few times over the years. 5.5. Table 3 shows the boiling point of some hydrocarbons. Describe how the boiling point changes as the number of carbons increase. So from minus 89 to 0.69125. The boiling point increases as molecular size increases. Page 20, which is 5.6. Give one condition used to crack hydrocarbons. There's 4 different options. You could say steam, or catalyst, or high temperature, or high pressure. Any one of those 4 would be sufficient. 5.7, balance the equation for cracking C6H14. Well, here we have C2. That means that over here we must get to C4 in total. So we're going to put a 2 in front. We're just going to double check that we have 14 hydrogens on this side now. 6 plus 4 is 10, plus 4 is 14. Give one reason why hydrocarbons are cracked. Again, 4 different options. To make smaller molecules, or to make useful molecules, or to meet the demand for small molecules, or to produce fuels. So when we crack, we're taking large hydrocarbons that we've got lots of. We are breaking them down into smaller hydrocarbons that we have less of to meet demand for fuels. Now, this question's a bit awkward because it hasn't given me the table of information. If you manage to get this, I will give you the answers. But it's thinking about the advantages of using wood rather than plastic. And we can kind of do this without the information. Wood is renewable. Is a good advantage. We can grow more trees. We can't easily make more oil to produce plastic. Wood uses less coal or oil or fossil fuel. It probably will still use some in transport, etc., but we're not using it to produce the product. And number 3, it uses less energy. There's a 4th one, if you wanted, which was it produces less waste as well. It produces less waste. Cool. I think we're on to question 6. Yeah, question 6 about chromatography. We are quite close to the end already, which is fantastic news. And we've been given an apparatus of chromatography where we're investigating the colours in brown ink. 2 errors are made by the student. Describe the problem each error would cause. So error number 1, there's 3 we're going to go through in total. The solvent is above the start line. So first thing to note here is that we're only told it's solvent, we're not told it's water, so it could be ethanol or something instead. And this is above the start line that we've got. So this means the ink will dissolve into the solvent. Error number 2, the start line is in ink, or it's not in pencil. And this means that the line will mix with the solvent, and it often means it will also travel up the paper, which is not helpful. If you want a 3rd one, it's the fact we have no lid, so the solvent may evaporate. Not normally an issue with water, but some other solvents we use will evaporate very, very easily. Question 6.2, we're on page 23. Give 2 conclusions we can make using this figure about the 4 colours in brown ink? Well, firstly, I'm noticing that this colour's in it, and this colour and this spot all match up what we found in brown ink. So one would be brown ink contains red, yellow, and blue ink. This is only 1 mark. If you said red and yellow, you would still only get 1 mark. A second one, brown ink does not contain green ink. Green ink is here. Green ink, there's no corresponding spot in the brown ink section. A third one, you could also say blue ink is most soluble because it travels the furthest up the chromatography paper, or red is least soluble. You do not get a mark here for saying that green is insoluble, because that is the next question. 6.3 asks us, why was the green colour still on the start line at the end of the experiment? It's because green is insoluble in the solvent. If it's insoluble, it won't dissolve, it won't then move up the paper. We then have to calculate an RF value. We've given some information. We need to actually work out the distance moved by the solvent. So we've been given this equation, and we're just going to substitute the values we got. So 0.24 is equal to 1.8 divided by distance moved by solvent. And that's actually our first mark, is just putting these values in. Mark number 2 is rearranging. So the distance moved by the solvent is going to be 1.8 divided by 0.24, which is going to give us an answer of 7.5 centimetres for our third mark. We're on to question 7. Question 7 is predominantly a 6 marker. There is also 4 marks of questions on the back of this. So it asks us to compare how easily potable water, or drinking water, can be obtained from wastewater or groundwater. There is probably quite a lot of different things you could write here. I'm going to give you quite a full answer, just to kind of get you thinking about what these differences would be. So wastewater, or to get from groundwater and wastewater, we're going to draw a small table. So we've drawn this small table with ground and waste. For groundwater, I'm just going to put a line there. It needs to be filtered. And the reason we filter is to remove insoluble solids. And then it is sterilised with UV or ozone or chlorine to kill bacteria. At that point, our groundwater is now potable. Conversely, for wastewater, we need to screen it, which removes large products. We then need to do sedimentation to go to sludge and effluent. We then need to do aerobic with oxygen to treat the effluent. Oops. We need to now sterilise whatever's left, again using ozone or chlorine or UV light to kill that harmful bacteria. And then we have anaerobic, so without oxygen, to digest the sludge. So what can we say about this? Wastewater is more difficult to obtain as more process is needed and and takes more time to make potable. Cool. Our last two questions. A scientist produced potable drinking water from salty water. What process can be used to produce this? This would be distillation. Electrolysis split ionic compounds. Filtration is to remove something insoluble from something soluble, and sterilization kills harmful bacteria using UV light, chlorine, or ozone. The salty water contained sodium chloride. They've collected 24 grams of sodium chloride from 150 centimetre cubed of salty water. What is the concentration in grams per decimetre cubed? So we need to firstly go from centimetre cubed, decimetre cubed, and then work out the concentration. To do this, we divide by 1,000. So we'll do 150 divided by 1,000 to get 0.15 decimetre cubed. And that would be mark number 1. Mark number 2 tells us the concentration is equal to the mass divided by the volume. So our mass is 2.40 divided by our volume, which is 0.15, to get 16. You can still get 2 marks if you do not convert this and do 2.4 divided by 150. You would still get 2 marks as your answer. And it would give you, what, 16,000 grams per decimetre cubed, or grams per centimetre cubed as an answer. Any questions about any of this, anything you want me to go through, please get in touch.